A mantis shrimp throws a punch that accelerates faster than a bullet from a gun. Not metaphorically, literally. At 23 meters per second, its club limb generates a strike force of over 3,500 newtons. That's enough to shatter aquarium glass. When that punch misses, the water around it vaporizes, producing a shock wave and a flash of light. A second hit from nothing. And the mantis shrimp isn't even close to the most extreme weapon in the insect world. In the next 8 minutes, we're going to look at 3 categories of biological weaponry that shouldn't be possible: extreme speed, extreme chemistry, and extreme pain tolerance that flips our understanding of evolutionary limits. Chapter: The Fastest Strike on Earth. The trapjaw ant closes its mandibles at 64 meters per second. That's 143 miles per hour. According to a 2006 study published in Science by Sheila Patek and colleagues at UC Berkeley, this makes it the fastest self-powered strike ever recorded for any animal. The jaws accelerate at over 100,000 g-forces. For reference, an astronaut during launch experiences about 3 Gs. A fighter pilot in a sharp turn hits 9 Gs. The trapjaw ant's bite mechanism sustains a force 11,000 times greater than that before it even makes contact. The muscle stores elastic energy like a compressed spring, then releases it in 0.13 milliseconds. That is 2,300 times faster than the blink of a human eye. But the jaw isn't just a weapon for catching prey. Trapjaw ants use their own strike to launch themselves into the air when threatened, converting predatory hardware into an emergency escape mechanism. A single jaw-to-ground strike can propel the ant 40 times its own body length vertically. No other insect uses its primary weapon as a parachute. Chapter: Chemical Warfare at the Nanoscale. The bombardier beetle produces a chemical explosion inside its own body, every single time it fires. Scientists first described the mechanism in detail in a 1969 paper by Thomas Eisner and Daniel Anashansley at Cornell University, and it took decades to fully characterize. The beetle has 2 internal chambers, one holding hydrogen peroxide and hydroquinone, the other holding catalytic enzymes. When threatened, it mixes them. The reaction reaches 100 degrees Celsius, the boiling point of water, inside its abdomen, building pressure that shoots a scalding jet from a rotating nozzle at the tip of its body. The beetle can aim 270 degrees and fire up to 500 bursts per second. That jet velocity exceeds 10 meters per second. A 2015 X-ray synchrotron study by Eric Arndt and colleagues, published in Science, mapped the internal valving in real time. The explosion is throttled by a pressure release system so precise it prevents the beetle from destroying itself with each shot. The chemical yield is equivalent to a 25 milligram explosive charge, small in absolute terms, but enough to kill an ant colony or deter a frog mid-swallow. Multiple documented cases exist of frogs vomiting bombardier beetles alive after ingestion, the explosion still firing inside the predator's stomach. Chapter: The Pain Index and Its Limits. Justin Schmidt, an entomologist at the Carl Hayden Bee Research Center, spent decades deliberately letting insects sting him to build a comparative pain scale. His 1990 paper, Hymenoptera Venoms, Striving Toward the Ultimate Defense Against Vertebrates, established what is now called the Schmidt Sting Pain Index. On a scale of 1 to 4, the bullet ant, Paraponera clavata, scores 4+, the only insect to exceed the scale's ceiling. Schmidt described it as, quote, pure, intense, brilliant pain, like walking over flaming charcoal with a 3-inch nail embedded in your heel. That pain lasts a minimum of 24 hours without any neurotoxic residue. The venom compound responsible, ponerotoxin, was isolated in a 1992 study in Toxicon Journal and later characterized in full by Alain Touchard and colleagues at IRD France in 2016. Ponerotoxin works by paralyzing voltage-gated sodium channels, the same ion channels that coordinate muscle contraction. The bullet ant's venom doesn't kill. It simply occupies the nervous system completely for a full day. Indigenous groups in the Amazon use bullet ant encounters as coming-of-age rituals. Boys weave gloves packed with sedated bullet ants and wear them for 10 minutes. They repeat the ritual 20 times before they're considered full warriors. Chapter: When Weapons Exceed Their Purpose. The Asian giant hornet, Vespa mandarinia, doesn't just kill, it dissolves. Its venom contains mandibilase, a protein-degrading enzyme not found in any other hymenopteron. A 2020 genomic analysis in Cell Reports by Keiichi Kakishima and colleagues sequenced the venom and confirmed 9 distinct toxic compounds, including a neurotoxin, a mast cell degranulator, and an enzyme that actively dissolves surrounding tissue after injection. A single hornet can kill a human without an allergic reaction. Repeated stings introduce enough toxin to cause multiple organ failure. But the hornet's most documented weapon isn't chemical. It's behavioral. When a scout locates a honeybee hive, it marks it with a pheromone. Within 30 minutes, a raiding party of 30 hornets can slaughter 30,000 honeybees in under 3 hours. Each hornet decapitates bees at a rate of 40 per minute. The bees cannot sting through the hornet's armor. Japanese honeybees have evolved one counter. They pile onto a hornet and vibrate their flight muscles, raising the pile's internal temperature to 47 degrees Celsius, just above the hornet's thermal tolerance. It's coordinated biological thermoregulation as active defense. Chapter: What We've Borrowed from Them. None of these weapons went unnoticed by materials science. The Mantis Shrimps Club, studied in a 2012 paper in Science by David Casalis at UC Riverside, has a helicoidal fiber architecture that absorbs impact without cracking, now being replicated in aircraft panels and helmets. The bombardier Beetle's explosion throttling mechanism informed a 2015 aerospace study on pulse detonation fuel injectors. Trap-jaw ant mechanics have influenced micro-robotics at Harvard's Weiss Institute. In each case, engineers found that these animals solve problems that took us centuries to approach. The question worth sitting with isn't why these weapons evolved. Selection pressure explains all of it. The question is, what else is out there? In the 5.5 million insect species we haven't fully cataloged yet, solving problems with biology that we haven't thought to ask about.